Assalamu alaikum dear students. I welcome you to the 13th lecture of probability and stochastic processes. So far we have covered discrete random variables and associated ideas. Particularly, we covered distribution functions of discrete random variables, their expected values, their higher moments, both regular and centralized, their conditional expectations, and covariance and correlation of two random variables, all for discrete case. Starting from today, we are going to thoroughly investigate the area of continuous random variables. These random variables are generated when the underlying sample space has uncountably many infinite possible outcomes. For such a sample space, there are uncountably infinitely many outcomes, and we take these outcomes and define events on them. We group them and define events and then assign probabilities to those events. Actually, we have covered such sample spaces and such unpredictable phenomena which do generate uncountably infinite number of outcomes. But we did that under some severe restrictions. For example, we assumed that all outcomes were equally likely, and we restricted ourselves to grouping those outcomes into events and finding the probabilities of the events. Since all outcomes were equally likely, the probability of any event was proportional to the number of outcomes in that event. And in case of those sample spaces which were subsets of real line, we only assigned probabilities to those events which corresponded to finite length intervals on real line. Similarly, for those random experiments which generated outcomes which were mapped on two-dimensional plane, we only assigned two probabilities to regions with finite areas. But our discussion was restricted to only those cases where all the outcomes were equally likely. Today, we are going to extend that discussion with those random experiments where the outcomes may not be equally likely. So let's start our discussion with the first topic of today's lecture, which is continuous random variables. Now that we know a lot about discrete random variables, we can easily extend the ideas to those experiments which generate uncountably infinitely many outcomes. So you know what random variables are. They are mappings, they are functions which take outcomes from sample space and map them to points on real line. Since we are discussing those sample spaces which have uncountably infinitely many outcomes, if the mapping of random variable is 1-to-1, then definitely the number of points that are getting mapped from sample space to real line are uncountably infinite. So how big an interval on real line do you need to map all the outcomes to real line? It happens to be that any finite length interval, no matter how small, no matter how large, would be enough. So as long as the range of this mapping, which maps points in the sample space to points on real line, is a finite length interval, you are fine. So the range of this mapping defines the values that this random variable can assume. These random variables are denoted by capital letters X, Y, Z, U, V, P, Q, etc. And the values they assume are denoted by small letters, small x, small y, small p, small q, etc., etc. So once you have this mapping which maps the outcomes which are uncountably infinitely many 2 points on real lines, then you assign probabilities to these points. And the probabilities on intervals and subintervals of this range of mapping define the behavior of unpredictable random phenomena. As I was saying, if this mapping, which maps points from sample space to point on an interval on real line, is 1-to-1, you will have uncountably, infinitely many points on real line. But if this mapping is many-to-one, even then there is a strong chance that the number of points getting mapped will be uncountably, infinitely many. The truth is, if this mapping is finite to 1, then the number of points on the range of this mapping will be uncountably, infinitely many. But you can devise a mapping which is from infinitely, uncountably, infinitely many to 1. Then from this continuous sample space, you can have a discrete random variable. But those cases will be rare, and we will not be talking much about those cases. So, from a sample space which has uncountably many, uncountably infinitely many outcomes, we map to an interval in real line, possibly the whole real line, and then we define events on this real line and assign probabilities to these events. That is how we are going to study continuous random variables. Sometimes it's possible to have a mixed type of mapping where some of the outcomes are mapped to a single point, giving this point a positive probability, and remaining outcomes are mapped to an interval on real line, giving uncountably, infinitely many points, where you can only assign probabilities to intervals and not to isolated points. Furthermore, it's quite possible that sample space itself is a portion of real line. In that case, outcomes are numbers, real numbers, and these outcomes themselves can be considered as values of a random variable. Quite often this is going to be the case, and then we will not distinguish between the outcomes of the random experiment and the random variable's values. The outcomes are values of the random variable. Let's revisit an example that we talked about a few lectures ago, which gives a sample space which has uncountably, infinitely many outcomes. In that example, we talked about a circular disk. I'm going to use this plate as a model for that circular disk. And we said, you take a circular disk like that and mark one point on the edge of this circular disk. And then you throw that disk on a graph paper. On that graph paper, there are x-axis and y-axis properly marked. And then when the disk comes to stop on that graph paper, you observe the orientation of that marked point. By orientation, I mean there is an x-axis and there is a line which joins the center to the marked point. And you observe this angle, the angle between positive x-axis and the line joining the center of the disk and the marked point. So this disk, when it comes to stop on the graph paper, can have this angle any value between 0 and 360 degrees. We are going to talk about a variation of this experiment. Suppose you drive a car and without looking at the actual position of the wheels, you drive your car for a reasonable distance and then you stop. After stopping the car, you step down and observe the position of nozzle on the front right wheel of the car. The nozzle is a pipe through which you put air in the tire. So that nozzle can take any value, and that value is also going to be in the range 0 to 360 degrees or 0 to 2 pi radians. Once again, we are going to measure this orientation of nozzle as angle between a line which is drawn through the center of the wheel and the line from the center to the nozzle. So this angle can have any value between 0 and 360 degrees. It's reasonable to assume that these outcomes, these observations of orientation of nozzle are equally likely. So nozzle is equally likely to stop at any of the points in the region where it gives an orientation angle between 0 and 360 degrees. So that is one observation. There is another observation that you can make in this experiment. Suppose when you stop the car, you get down and you see the position of the nozzle, but you observe the height of nozzle from the lowest possible point. Suppose this is wheel, and if the nozzle is at the bottom, that is the lowest possible point. Then nozzle can be anywhere on the periphery of the wheel, and if it is here, then the vertical distance between this point and the point passing through the lowest point is your observed random variable. Both of these random variables belong to intervals on real line. If we are measuring the angle in radians, then the orientation is a point between 0 and 2 pi. And if you are measuring this vertical distance between the position of the nozzle and the lowest possible position of the nozzle, this is distance, and this can range between 0, representing the lowest point, and 2r, where r is the distance between the center of the wheel and the nozzle. So this random variable can assume any value between 0 and 2r. We assumed that orientation, the first observation where we measure the angle, is an experiment where all outcomes are equally likely. If we assume that and assume it to be true, then question is, what about this other random variable, the other observation that we make, which is the height of the nozzle from the lowest possible point? And this value between 0 and 2r, is it equally likely? Is it equally likely for the nozzle to be at height, say r, or r by 2, or 3r by 2, or 2r, or 0? This question will be answered towards the end of this lecture. One thing you should note is that these two random variables, the orientation of the nozzle and the height of nozzle from the lowest possible point, are related to each other. If we call x the random variable, which is the orientation of the nozzle, and you call y the random variable, which is the height of nozzle from the lowest possible point, then x and y are related. And you can figure it out using simple trigonometry that y, the height, as a function of theta, the angle, positive angle from positive x-axis, are related by equation that y is equal to r plus r sine theta. This has been worked out in your class handouts, but you should try to do it yourself. So this random variable x and this random variable y are related, and if we know something about the behavior of random variable x, which is that all outcomes are equally likely, we can make deductions about the behavior of random variable y. Most importantly, will this random variable y have outcomes which are equally likely or not? Please note that for this experiment, you have to assume that the nozzle is represented by a point with 0 width and 0 height, and all these measurements are ideal with infinite precision. Before analyzing this example of position of nozzle and its height in a more systematic manner, let's look at a few other examples where we get continuous random variables. The example I'm going to take is the one we talked about a few lectures ago, where we had a floor, and on that floor we marked lines, parallel lines with a known spacing d. And on that floor we threw a circular disc. Once again, I'm going to take this plate as a model of that circular disc. So we have a floor with parallel lines, and on that floor we throw a disc, circular disc with known diameter, and then we are interested in events like whether the circular disc touches a line or not. We are going to go beyond that, and for this we are going to assume that the line spacing is exactly equal to the diameter of the plate. Assume this diameter to be d, so diameter is d units, and the spacing between two parallel lines on the floor is also d units. This implies that when the plate comes to rest on the floor, it cannot touch two lines and it must touch one line always, assuming that the lines are ideal, that is zero width. If that's the case, then the first random variable that we can be interested in is the distance between the center of the disc and the line below this center. You can select any reference direction. You can say if I'm standing here and I'm throwing disc, then this random variable x is the distance between the center of plate and the line towards me, the next line. So this random variable x can have values which are continuous, uncountably infinitely many, and they always fall in the region 0 to d. So if this is the line, then the center can be at a distance d, or it can be distance 0. So this random variable x lies in the region 0 to d. Next random variable that we can define is the distance between the center of the plate and the nearest line. The difference between the two cases is that previously we were measuring the distance from the center of plate to the line below it. Even if the center was very close to the line above it, we were still measuring the distance below. But now, as soon as this center goes closer to the top line, we measure this distance. And when this plate is in such a way that it is closer to the lower line, we measure this distance. And it's very obvious that this random variable, we can call it v, is also continuous, and it assumes uncountably infinitely many values in the region 0 to d by 2. You should figure it out and draw some diagrams to figure this out. The next random variable that we might be interested in is the arc length of the smaller partition. When I say partition, I mean this circular disc is always going to touch a line. Suppose line is like this, then smaller partition is the top one, and if this plate rests such that the line is like this, then smaller partition is the bottom one. Let's assume this edge of the table is our line and this circular disc rests in this fashion. In this case, when the top partition is the smaller one, we are interested in this arc length. The arc, which is the arc of the smaller partition. We can call this random variable w, and this random variable w is associated with random variable x or v previously defined, and you can figure it out by again using simple trigonometry, and the formula is that this random variable w is equal to d, which is the diameter of the plate, d times cosine inverse of 2v divided by d. This has been worked out in your class handout and you can see it there. The next random variable that we can define is the area of this small partition. So when the circular disc comes to rest and it is getting divided into two partitions, we observe the area of the smaller partition as our random variable. The last random variable that we are going to define for this situation is the ratio of two areas, where smaller area is in the numerator and the larger area is in the denominator. So the line cuts the circular disc. There are two partitions. one is smaller, one is bigger. If line is like this is smaller partition, this is larger partition, and your random variable is ratio of this area divided by this area. And if the line is like this, then the random variable is ratio of this area divided by this area. All these random variables could be interesting for academic purposes because they will highlight a certain aspect of continuous random variable. That is, how different random variables defined for an underlying random experiment are related to each other. How, knowing one, we can find characteristics of the other, particularly the idea of one of them being equally likely and the others being not. We will thoroughly analyze the random variables defined for location of circular disk over a partition floor in coming lectures. One last example about the continuous random variable is the example of customers entering a certain restaurant. Here, we are not going to count the number of customers in a certain time interval, but we are going to be interested in the inter-arrival time, the time between arrival of the first customer and the second, the time between arrival of the second customer and third, and so on and so forth. For this kind of experiment, we have to assume that this arrival is instantaneous, even though when customer enters a restaurant, his whole body takes a few milliseconds to actually complete the process of entering, but we are going to assume that this entrance is instantaneous. Other examples could be the inter-arrival time of telephone calls to a telephone operator, or inter-arrival time of two HTTP or FTP requests on a server. So all these unpredictable random phenomena gave continuous valued random variables. Why continuous valued? Because we are measuring inter-arrival time, and if we assume that we can measure the inter-arrival time with extreme precision, then this inter-arrival time can be anything. It can be 2.3579 seconds, or it can be 17.53452 seconds, or any number, any real number that you can imagine. Assuming the example of customers entering a restaurant and observing the inter-arrival times, which are continuous valued random variables, can you make a guess if this random variable has equally likely outcomes, or if certain outcomes are more likely than the others? I hope you can get a feel that this random variable is not equally likely. It is highly unlikely for an inter-arrival time to be microsecond. Even though we are allowing this random variable to take any positive real value, but it's not possible physically for two customers to arrive within a microsecond of each other. Similarly, if the restaurant is quite popular, then it is highly unlikely that the inter-arrival time is 2 hours, that after one customer goes, for 2 hours nobody comes in. It's highly unlikely. The inter-arrival time will be more likely in the range of 5 to 30 seconds. And it will be very less likely for inter-arrival time to be either in microseconds or hours. To analyze these continuous random variables, where the random variable takes values in a small interval on real line or whole real line, but the number of values that random variable can assume are uncountably infinitely many, we need a tool called probability density function. We did work with a variation of probability density function when we were dealing with discrete random variables. There we called it probability mass function. As probability mass function describes the behavior of discrete random variable, that is, what are the values that discrete random variable attains and with what probability these values are attained. As Probability mass function can handle those discrete random variables which have equally likely outcomes, or those variables which have outcomes which are not equally likely. Similarly, the probability density function for continuous random variables is going to describe the behavior of continuous random variable, and it's going to allow us to work with those continuous random variables which have equally likely outcomes, as well as those continuous random variables which have outcomes which are not equally likely. If you remember, when we were talking about discrete random variables, we talked about a rigid rod and weights hanging on that rigid rod. This was discussed in the context of expected value, where the rod was pivoted at 0 and the net torque on the rod with all those weights hanging on the rod using threads was equal to the expected value of the random variable. We are going to use a similar analogy, but this time the rod is not going to be pivoted anywhere. Actually, the rod is going to be stationary, stable, and supported by two wedges, two sharp supporting points which are outside the range of random variable. There is an underlying space, there is a portion of real line where the random variable maps these outcomes, and our supporting wedges will be outside this range. The rod is rigid and it is supported and it is stable. Then the discrete random variable can be modeled as weights hanging from this balanced supported rod at locations which are the values which random variable attains, and the amount of weight is equal to the probability of that value. Then the probabilities of different events defined on this rod, which is a portion of real line, is equal to summation of all the weights which fall in this interval. All this is shown nicely in the slide that you can see, where for the case of discrete random variable, there are 3 weights hanging at 0, 2, and 3, and the values of these weights are 0.6, 0.3, and 0.1. So the discrete random variable takes 3 values, 0, 2, 3, with probabilities of 0.6, 0.3, and 0.1 respectively. For this random variable, if you want to find the probability of this random variable being in the range 0 to 2, both points included, then this event has a probability which is sum of 0.6 and 0.3, which is the 2 weights hanging in this interval between 0 and 2, both points included. We are going to extend this analogy for continuous random variables. We are going to have the same rod. Actually, we are going to have a bar with square or rectangular cross section. And we are going to support this bar on 2 wedges which fall outside the range of random variable. We are talking about continuous random variable. So there is a sample space, and this sample space gets mapped to points on real line with this continuous random variable. And if you assume that the range of this mapping is finite and we support this bar at 2 points which fall outside this range, then the behavior of random variable can be modeled as loading, not through threads and isolated hanging weights, but loading with sand, a layer of sand, a little wall, a little dam, a little dike of sand built on top of that bar. You can see this in your slide, that due to this continuous loading, you take sand, say 1 kilogram sand or any one unit, and spread it over the bar. Then the total loading is 1 kilogram. But there is no isolated point where some of the sand is concentrated and loading the bar. It is spread over a range. So the amount of load on a certain isolated point is 0. But amount of load due to this dike of sand on a certain non-zero length interval is all the sand which is above this interval. So the probability of this event, this random variable, continuous random variable having values between 2 points which define an interval with non-zero length, is equal to weight of all the sand over the bar which falls between these 2 points. And what's the probability of the whole range? It is 1, which is equal to the weight of total sand. So this analogy will be used for analysis of continuous random variables, where the amount of sand represents the weight and the weight represents probability, and you can only define probability for non-zero length intervals. One thing that you should remember about this modeling of continuous random variable with a dike made of sand is that it is okay if the height of this dike varies as we move from one wedge to the other. So if this is the real line, which is where the random variable assumes values, and you have a finite width bar, then the height of the dam can vary in this direction. But if you move in this direction, the height should not vary. It should be flat and it can vary like this. In this case, if you observe this dike perpendicularly on, then you will only see the top surface, and this dike can be represented as a function which is one-dimensional function from R to R. In that case, you can model this varying heights with a function, and the probability of any interval on real line will be the total area under this curve, the function between the 2 points. Once again, the total area for an isolated point is 0, because when it's isolated point, the width of interval around that point is 0. So no matter how high this function is, the total area will be 0. So if the interval over which you are trying to find the probability is finite, then the total area under the curve bounded by these points is going to be the probability of the random variable being inside this interval. This is exactly what probability density function is. Probability density function of a continuous random variable is a function which defines the relative probability of different outcomes. And the simplest case is that random variable which has equally likely outcomes. We are going to take the same example, that of circular disk getting thrown on a floor with parallel lines. Assuming again that d is the diameter of the disk and d is also the spacing between the lines, then the random variable, the first random variable that we talked about, was going to assume values between 0 and d, and all these values were equally likely. To model this continuous random variable using probability density function, we'll have a function which is constant, which does not vary its height as it moves from the lowest possible point that is represented by the value of random variable to the highest possible point that the random variable can take, which in our case happens to be 0 to d. So probability density function for this random variable is a constant height line between 0 and d. Question is, what should be the height of this line? As you know, the probability of the whole sample space or the whole range of random variable must be equal to 1, because it represents the probability of a certain event. So the height of this constant height function should be such that the total area under this curve is 1. So if the extent over which this random variable is defined is d, then the height must be equal to 1 over d. Only then the total area will be 1. This is graphically shown on the slide that you can see, where the PDF is represented by a constant height line which runs from x equal to 0 to x is equal to d, and the height of the line is 1 over d. And one interesting event where we want to find the probability of this random variable being between x1 and x2 is equal to the area under the curve, which height 1 over d, bounded by vertical line x is equal to x1 and x is equal to x2. It happens that this area will be x2 minus x1 divided by d, which is the height of that function. You can find probabilities of other interesting events from this PDF, where the probability of any event is the area above the interval which represents that event. Another interesting idea related to probability density function is the idea of cumulative distribution function. This is probability of events which are parameterized by a single parameter x or t, whatever you choose, and as this parameter moves from minus infinity to plus infinity, you find a probability of all values which lie between value of this parameter and minus infinity. So as this parameter moves, you find probability of the random variable with values from minus infinity to that parameter. This is called cumulative distribution function, and this has been discussed in the context of discrete random variable as well, where the CDF or cumulative distribution function made jumps because discrete random variable assumes non-zero probability values at isolated points. So as the parameter passes through that points, the CDF makes jumps. In the case of continuous random variables, CDF usually does not make such jumps, and it monotonically rises. As the parameter moves to the right, more and more outcomes are included in the event where random variable is assumed to be in the range from minus infinity to the value of that parameter. As more and more outcomes are included, the probability becomes higher and higher. Eventually, this probability becomes 1. So cumulative distribution function for a continuous random variable is usually a continuously and monotonically increasing function of parameter x or t or y, whichever you choose. PDF and CDF are related to each other. As I told you, to get to CDF, you find probabilities of all the events which are from minus infinity to the value of parameter, and this is equal to the area under the curve from minus infinity to the value of that parameter. Hence, to get CDF, you integrate PDF from minus infinity to the value of that parameter, and to get PDF from CDF, you differentiate the CDF and you have your PDF. These two formulas are shown on the slide, and you should note a particular observation. That is, for the case of the formula of CDF, I have not used the conventional notation. I have used a dummy variable tau. So CDF, which is parameterized by x, it is capital Fx parameterized by small x. It is equal to integration of PDF from minus infinity to x, and then in the integration, instead of using x, which is the norm, I have introduced a dummy variable tau. So integration is with respect to tau, a dummy variable which is going to vanish away at the end of integration, and only thing surviving will be the parameter x, which appears as the upper limit of integration. Now that you know about PDF and CDF of continuous random variables, let's use these to find probabilities of different interesting unpredictable phenomena which give uncountably infinitely many outcomes. One way to analyze the behavior of continuous random variables is to explore the relationship between two different random variables. when we were discussing the problem of the orientation of nozzle and its height from the lowest point, or the center of the disc on that lined floor versus the areas and the ratios of areas, we found that all these random variables on underlying common random experiment were related to each other. And if we know the behavior of one random variable, and if it is equally likely, we can explore the relationship of this random variable with the other random variable to find the probability density function or CDF of the other random variable. So let's explore this option of going to PDF or CDF of a transformed random variable when we know exactly about the behavior of the original random variable. We are going to take the example of equally likely variable, which was equally likely between 0 and D, and it was modeled as the location of center of the circular disk from the line below it. If our original random variable is called x and it is equally likely between interval 0 and D, then we can define a new random variable y, which is equal to 2x plus 1. This is a linear kind of transformation. So whatever the value of x, you can get value of y by multiplying the value of x with 2 and adding 1. First, let's look at the range of values of y. We know the range of values of x is between 0 and D, and the transformation is 2x plus 1. So the range of values of y will be 1 to 2D plus 1. The total width will be 2D starting from 1 to 2D plus 1. This has been shown in the slide, and you can look at the slide and see what happens to point x1 and x2 as shown on the PDF of the original random variable x. Point x1 gets mapped to new point, which is y1 equal to 2x1 plus 1, and point x2 gets mapped to point y2, where y2 is 2x2 plus 1. The distance between the 2 points here was x2 minus x1, and here the distance between 2 points is twice that. If it was x2 minus x1 here, it is 2 times x2 minus x1 here. So all those outcomes between x1 and x2 get mapped to outcomes between y1 and y2. Since this is a linear transformation, and I leave it up to you to have this proof that for linear transformation the shape of probability density function does not change, it just gets stretched or squeezed depending upon the transformation. If the transformation is expansive, it expands the values, then the range gets enlarged, and if this transformation is contractive, the range gets reduced. So we are going to assume that it's true that the random variable y will also be equally likely. It will have its outcomes equally likely, and they will range from 1 to 2D plus 1. Since these outcomes are equally likely, they will be represented by a PDF, which is a flat function. Question is, what's the height of this function? Once again, remember the total area should be 1 and total width is 2D, so the height will be 1 over 2D. Now look at the probability of the event between x1 and x2. It was x2 minus x1 multiplied by 1 over D. Here the same event gets mapped to all the outcomes between y1 and y2 with width is equal to twice that of x2 minus x1, but the height half. So total probability of y being between y1 and y2 is same as x being between x1 and x2. For this simple transformation, the shape of PDF does not change. It gets expanded, but its height gets lowered. Other transformations which are not linear are usually more difficult to handle, and we are going to discuss such a transformation next. Let's analyze that problem we mentioned in the beginning of the lecture, that is behavior of the random variable which represents the height of the nozzle from the lowest possible point. We are going to analyze this as a mapping between one random variable and the other random variable. The random variable x, which was previously represented by theta, is the angular orientation, and random variable y is the height of the nozzle from the lowest possible point. And the mapping between x and y is that y is equal to r plus r sine x. X was previously called theta. So under this transformation, under this mapping, which is certainly non-linear because of the inclusion of sine of x, what happens to the values and their relative probabilities of random variable y, knowing that random variable x is equally likely to occur between 0 and 2 pi radians. To analyze this, let's look at the nature of this mapping. Is this 1 to 1 or is this multiple to 1? As you can imagine, if the nozzle is at the lowest point, there is only one lowest point where the nozzle can be. But if the nozzle is above this lowest point by a value y, then there are 2 points. If this is the lowest point, then there are 2 points where the height could be y. One is to this side, other is to other side. So these 2 points give me the same value of height from the lowest point. So this mapping is 2 to 1 for most of the points, except for the lowest point and the highest point where this mapping is 1 to 1. Even if this mapping is 2 to 1, the number of points are uncountably infinitely many, and they lie in the range 0 to 2r, where r is the distance between nozzle and the center of the wheel. So we know the probability density function of x or theta, and we know the transformation. So how do you find out the probability density function of transformed random variable y? The idea is that you do not try to find probability density function. If you try to find probability density function, then you are trying to find the probabilities of these mapped points, and we do not assign probabilities to individual points when we are dealing with uncountably infinitely many points. As we said, in y there are uncountably many infinitely points lying between 0 and 2r. So what do? You transform the cumulative distribution function. You first find CDF, differentiate it, and then get PDF. And it's very easy to find CDF of this transformed random variable y if you know the behavior of random variable x or theta, which is equally likely to occur between 0 and 2 pi. So what's the minimum value of y? It is 0. What's the maximum value of y? It is 2r. Now you try to find the probabilities of events parameterized by y, where y is the height which goes from 0 to 2r. So you take a certain value of y and find all the angular locations which give you a height between 0 and y. And probability of all these angular locations found from the probability density function of x gives me the probability of the event that y belongs to interval 0 to this y. If you increase this parameter y, you will get more and more and more and more points in the angular orientation, and the probability of this, which is the arc length divided by 2 pi, which is the total arc length, gives you the probability of this event, which gives you an interval in y between 0 and a certain value of y. This has been worked out in your class handouts, and you can go there and see it. And it turns out that the CDF of this transformed random variable is not a linear function. It increases rapidly in the beginning, then increases slowly and again increases rapidly, and then it becomes 1. And if you differentiate this CDF, you will get a PDF representing the relative probabilities of these heights of nozzle, this variable y. And it happens that relative probability of y is very large when y is close to 0 and very large when y is close to 2r. So PDF is in the shape of this, where it is very high close to 0 and very high close to 2r and low in between. And this is agreeable, this is conceivable, because when you are taking a small height near 0, suppose 2% of the total height 0 to 2r, you are taking a large arc which is going to contribute towards that event. And similarly, when you are taking interval close to 2r, in a small interval there is a large arc. And when you are talking about intervals close to r, since the arc is perpendicular, for a small region there will be small length of arc contributing to that event. Hence, probability density function of this random variable y, which represents height of the nozzle from the lowest possible point, is not uniform. The PDF is high towards 0 and it's high towards 2r and low in between. And CDF is not linear, it increases rapidly close to 0, then increases slowly and again increases rapidly. Certainly, you can use this idea of transforming a known random variable to another random variable to find PDF and CDF of transformed random variables. In next lecture, we are going to explore this idea with more rigor, and we are going to analyze those random variables mentioned today, where we throw a disk and take area of the smaller partition of the disk or the ratio of smaller area and larger area. This will be done in next lecture. Till then, I wish you goodbye. Thank you.